Hi again. In this problem, I'm going to use Coulomb's law to solve a problem where we have 4 protons in the corner of a square. And the question is, what is the force on the charge in the upper right corner? So this is off of the worksheet that says honors Coulomb's law practice. And this is actually, despite what this says right here, it's actually number 4 on it. Just kind of copied over as 1. But anyway, we're looking at the superposition principle, which means that, when you have multiple things happening in one spot, how do you solve that out? So that's what superposition means. But anyway, either way, we're finding out the force. So let's go ahead and do this. What I'm going to do, I think I got shapes. And I'm going to go ahead and use my shape. I'm going to use a square. And we're going to use the program because I can to draw a nice square like that. And why not? I can draw circles. You know what? No, I'm not going to do that. I'm just going to draw them. Okay, so here's our square. Each side is 1.52 times 10 to negative 9 meters. That's that missing spot right there is times 10 to the negative 9th meters. And these are protons, which means it's implied that, the charge of a proton is the 1.6 times 10 to the negative 19. So I'm going to go ahead and throw some protons at the corners of this triangle like this. The square. And the question is, what is the force up here in the upper right corner? So I'm going to call this one Q1, Q2, Q3, Q4. Now, what I'm doing here is just a way to organize things. This is not necessarily my method, but this is just a method to help you keep things organized as you do this. So I could have went Q1, Q2, Q3, Q4, or however, I can do this any way I want to. So you can label yours anyway. It's just an organizational thing. So in this problem, we are going to have some x and y's, but the fact that we have a symmetric object means that we could take some shortcuts here and things will cancel out. So as always, my first step is to analyze the direction and draw them out. So you can kind of get a visual of what's going to happen here. So let's go ahead and do that. So Q2 is going to be, so remember these are all protons, so they're all positive charges. So I'm going to go ahead and just put a little positive there just to remind us that these are all positives. So Q2 and Q1, I'm going to ignore these. Q2 is going to push this upward like this. And this is a force of 2 onto 1. So ignoring the other two, this is going to push it directly upward. Now the direction it pushes is in a straight line with the charge, so it can only push up or down. In this case up because they're like charges, they push away. Let's look at Q3. Q3, if we ignore the other two charges, is positive, so this is also going to push away. But the away direction is going to be pointing like this. So this is force of 3 onto 1 because it can only push in a straight line. And I try to draw it as best as I can here, but note that this is a straight line. And then lastly, I have Q4. Q4 is positive, Q1 is positive, it's going to push away as well. This is the force of 4 onto 1 like that. So here we have our system here. And the question is, we're being pushed up, we're being pushed this way, we're being pushed up and to the right. Ultimately, what we're going to do, the question is, how do all these forces pretty much add up? And my prediction is, well, I'm going to be pushed up and to the right and pushed up to the right. So my prediction is we're going to be pushed in this general direction. So that's kind of just me thinking about, how will these pushes interact with each other. Okay, so step 2 is we're going to find the strength. No signs, no nothing. How big is the force? So let's go ahead. So force of 2 onto 1. Okay, Q 2 q1 over r squared, like that. So here we go, 8.99 times 10 to the 9th newtons meters squared over coulomb squared, just like that. Q1 and Q2 are protons. All of them are the same, even though I label them as different. They're all the same, protons. So the charge is just going to be charge of a proton for both of these. You can also technically, I didn't put the coulomb there. You could technically square this because they are the same number, or write it out. It does not matter. Now the distance from here, Q2 to Q1, is 5.12 times 10 to the negative 9th, because a square means all the sides are the same. And there we have it. So let me go ahead and punch these numbers into my calculator. Oops, e to the negative 9th squared. And what I get here is 9.96 times 10 to negative 11th, and the units for our force are newtons, like that. So that's the force of 2 onto 1. That's what we just solved for. Let's do the next one, force of 3 onto 1. Okay, Q3, Q1, r squared. So let me just label this 2 to 1, and I kind of made that here, but that's this distance from here to here, force 2 to 1. So it's not 21, it's just distance right here. However, if you look at force of 3 onto 1, it's the distance between here and here, right? That's how far apart they are, not this number. That's the sides. And what I need to find is this dotted line. So what I say to myself is, okay, how do I find this dotted line? Well, if I look at this, this kind of looks like a triangle, right? From here to here to here, right? Drawn not perfect, but you get the idea. That's a triangle, and if I pretend this is my right angle, then this dotted line represents the hypotenuse of the triangle with the sides of a square. So I'm going to have to do a side step here and figure out this yellow triangle. I'll leave it in there. So I'm going to call this R3 to 1 because that's the distance between the two. And R3 to 1 is basically me solving the Pythagorean theorem. I have one side, second side, I got to find that. So R3 1 squared is going to be 1.52 times 10 to the negative 9th meters squared, plus the following, the same number, squared like that. E to the negative 9th squared, plus the same thing. And then to get that by itself, I need to square root. So I went ahead and just solved this whole thing out. (2.15 to the negative 9th meters is this leg right here. Okay, so I needed an extra step to do that, and it looks like it makes sense because it is bigger than my two sides, so it looks good. Okay, now we can finally plug this into our calculation here. So it's the charge of a proton for both of them. These are the same values. You can plug those in like that. All divided by this one squared like that. And because I don't have any room, I'm just going to put the answer down here. So I'm going to type that in 8.99 e to the 9th, 1.6 e to the negative 19th, times 1.6 e to the negative 19th, 2.5 e to the negative 9 squared. What I get is 4.98 times 10 to the negative 11th newtons. We're in the same ballpark. That's always a good thing because we're using similar numbers, so we're good here. What I'm going to do is just box these because, as you can see, we have a lot of math going on, and I'm going to need this for later. So I just want to go ahead and have these ready to go. Okay, so we just did that one. We found that one. Now we got to find this one. So the force of 4, 1, KQ4, Q1, R4 squared. So it's this. And it's going to be that charge of the protons. And the distance between these is nicely done already. We don't have to do any geometry because they gave us the distance from here to here, which is the 1.5. Squared. Okay. Well, shortcut time, because if you notice, this calculation is exactly the same as this calculation. So cool. I'm gonna not even plug that into my calculator, and if I did, I should be able to get the same value anyway. But the force of 4 into 1 is the same as the first one. If you don't believe me, you can go ahead and calculate it through, but you should get the same value right there. Okay. So now what I gotta do, at this point, now that I got all these three, my next step, oopsie, there we go. My next step, step 3 here, is to find the forces in the x and in the y of each. Now we definitely need to do that because we have an up, a right, and an up and to the right. So these we can break down into our x and y components. So the way I'm going to do that is actually going to help my drawings originally. But step 1 is very important because this helps me visualize what's going on here. So when I analyze this, I see that force 2, 1 is directly upward. That means that this is a y value and has no x value. So technically this is my y value here. And since it's going up, it's positive. And quite technically, f2x 21x is 0. There's no y component. So if you notice, I don't need to do any calculations for this. This is based on logic right here. And I'm going to skip down to this one because for the same logic, notice that it's completely horizontal here and pointing to the right. Because this is completely to the right and horizontal, it has no y. So this means it's an x component because it's on the x-axis. It's also positive because it's going to the right, which means my force in the y is 0. So that's easy. Well, not easy, but at least easier than this, relatively speaking. The question then is this one. This one's at an angle, so that's when I need my sines and cosines. So when you use sines and cosines is when you don't have something perfectly right, perfectly up, left, or down. So that's the one that's going to take a little work. So I'm going to do that one over here. Like I said, I usually take it out of the problem because you can see there's just so much stuff going on here. So this right here represents that force. Now, the upward arrow represents the strength of this. This is the number we got earlier, this one right here. This is the hypotenuse of the triangle that we're trying to find here. And the question is, what is this piece and this piece? Now, the direction of arrows depends on this arrow. So notice that in order to make this arrow, I have to go to the right and up, which tells me that these are going to be positive in the end. So I need to find the y piece and the x piece here. So when I'm thinking about this, I'm missing an angle right here. So that's another thing I need to find. So I don't have it in the problem directly, so that means I need to find it indirectly. So what I know about squares is that this is a right angle right here. So that means it's 90. So if I cut it in half, that means this must be 45. So I'm using the geometry of the square to help me find the angle. So this is going to be 45 degrees. Okay, so I need to find my x and y. So my fx is, notice that it's next to or adjacent from my angle, which means that it's going to pop out a cosine factor. So it's going to be the hypotenuse times cosine of the angle if you do SOHCAHTOA. So I do SOHCAHTOA pretty fast, so if you need help with that, just let me know. But usually when I have this case and I have the hypotenuse, it's going to be the hypotenuse times the angle right here. So I'm going to go ahead and do my fast trig here. Hypotenuse times cosine 45. And then with the similar logic, this is the opposite here. So with that said, then this is going to be Fy, when it's opposite, it's going to be sine. So Fy here is going to be the sine. So let's see, 4.98, the hypotenuse times sine 45. So I'm going to go ahead and plug that in, 4.98 e to the negative 11 times cosine 45. 3.52 times 10 to the negative 11th newtons, and it's going to the right, so this is a positive value. Alright, so then what I have here, if you plug this in, you'll get the same answer. Or if you know that anytime you have a 45-degree angle, you're going to get the same value. Not only are we going to get the same value, but it's also positive because it's moving up. So it's positive because this is moving right, and positive because it's up. Okay, now that we have this case right here, our next step in our list of steps is we're going to add up, oops, I keep doing that, sorry. Or we're going to add all the x's and y's. And then after we do that, we find our make a triangle. Oh boy. All right, I'm going to go ahead and just come down here. So that's when I make that chart, right? The XY chart. And what you put in this chart is a force of 2 on the 1, 3 on the 1, 4 on the 1. And then this bottom line is the total. The force of 2 on the 1, go ahead and get that value. The y is a 9.96 and the x is 0. So I'm going to go ahead and do that. So x is 0. This is 9.96 to the negative 11. F31 we have right here. They're both the same value. Oops, let me write that the right way. It's 0.52. There we go, 3.52. Sorry about that. Okay, both positive, so I'll leave them like that. In this case, our x value for the fourth one is this one right here. And this one is 0. So let me add these up to get our totals. 3.52 e to the negative 11th plus 9.96 e to the negative 11th, oops, e to the negative 11th, 1.35 times 10 to the negative 10 newtons here. And when you add these up, surprise, you get the same value, like that. So remember what we're doing, we're adding the x's and y's, so these are our total x's and y's. So step 5 is we're going to make a triangle with our total x and total y to find the hypotenuse, which is the net force, and the angle. So that's my final step here. So F net is what I'm finding. And we have the legs of this triangle. Okay, so I'm finding the hypotenuse. So the F net in one step. I like doing the Pythagorean in one step. The square root of the sum of the legs squared. Oops. This number we're squaring it. This number we're squaring it. Oops, not 10th. Go ahead and just fix that. Keep checking. 10 newtons squared. So I'm going to go ahead and solve this out. Alright, I get 1.91 times 10, negative 10 newtons, like that. So that is my net force. So that's what I solved. This is the hypotenuse here. Now I want the angle. Now, the trick is, this is a 45-degree triangle because the two legs are the same. So that's the easy way to do this. Or you can always take the tan of your total y, divide by total x. And when you do that, you will find that you will get the same answer. So I'm going to just humor ourselves here, just in case you didn't know that trick. You will find that this technique will work. And there you have it. This is 45 degrees above the x-axis here. Now you do want to add a little bit more than just 45 degrees because it does matter where you take that 45-degree angle from. So make sure you make a note here about where you're taking your angle from. It could be anything as long as you're labeling it properly. So coming back up here, what we found is that the force, this basically and this combined with that, and we get a force net that looks like this, which is also 45 degrees right here. So what does this mean? So it means if I put these four charges together and kept assuming that this one's locked and fixed in place, if I put this here and let it go, it would push out straight that way. And I hope it makes sense to you because we get a push from this one, and this one. So that's our combined forces on that. And that's what we solved in this first problem, this problem with the 4 protons in a square.